All right, let's dive in. Today, we are tackling one of the most powerful and, let's be real, one of the most feared features in all of programming, C++'s manual memory management. We're going to turn that fear into some serious mastery. Anyone who's ever written a line of code knows this feeling deep in their bones. Programming is tough. And C++ has this reputation for being the final boss, mostly because of how it handles memory. But that reputation, it's really built on an older way of doing things. So let's break down the problem to understand the brilliant solution. First things first, you have to understand the core bargain of C++. The language gives you ultimate power, ultimate performance, but in return, it gives you ultimate responsibility. And nowhere is that more true than with memory. So, what does direct control actually mean? It means you can manage every single byte your program uses. This is exactly why C++ is the king for things like high-performance video games and even the operating system you're using right now. But it's also like walking a tightrope without a net. One tiny misstep, and your whole program can just crash and burn. Okay, so to really get a handle on this balancing act, we need to know where our program's data actually lives. See, it's not just one big bucket of memory. There are two totally different worlds where your data can end up. On one side, you've got the stack. Think of the stack like a perfectly managed, self-cleaning apartment. The second you're done with it, poof, it cleans itself up automatically. It's fast, it's orderly, it's safe. But it's also pretty small. Then you've got the heap. The heap is like this vast, open frontier. You can claim as much land as you need for as long as you want, but, and this is a huge bite, you are responsible for everything. There's no cleanup crew coming to help. This is the Wild West, and to survive out there, you need the right tools. And the classic tool for venturing into that Wild West of the heap, that's the raw pointer. This little guy is where C++'s dangerous reputation really comes from.
So what is a pointer? Simple. It's not the treasure, it's the treasure map. It doesn't hold the value 100, it holds the address, the specific location in your computer's RAM, where that value 100 is being stored. And that little map is what lets us work with memory out on that wild frontier, the heap.
And this is the pact you have to make. It's a three-step dance. First, you use the keyword new to ask the system for a chunk of memory. Second, you use that memory with your pointer. And third, this is the part everyone gets wrong, you must remember to manually give it back using delete. You're on the hook for every single step. This is the single most important rule in classic C++ memory management. And it sounds simple, right? For every new, just call delete. But in a program with thousands, maybe millions of lines of code and all sorts of complex logic, it is incredibly easy to forget. And when you break this rule, disaster strikes. And this is what happens when it all goes sideways. If you forget to delete, you get a memory leak. It's like a tiny dripping faucet that eventually floods the whole system, eating up all your RAM. If you try to use a pointer after you've deleted its memory, you get a dangling pointer. It's like trying to cross a bridge that you've already demolished. And if you delete the same memory twice, that's pretty much like setting off a bomb inside your program. Immediate crash. This is the peril of manual memory. So for years, programmers just struggled with this. But then they came up with a really clever idea using C++'s own features against the problem. What if you could create objects that could manage their own life cycle and clean up after themselves? It all starts with a constructor. Think of this as the object's birth certificate. The moment an object is created, this special function runs automatically to set everything up and get it ready to go. It's the setup phase. Well, if there's a special function for an object's birth, it just makes sense there's one for its death, and that's the destructor. When an object is no longer needed, when it goes out of scope, this other function runs automatically to handle any last-minute cleanup. And this automatic cleanup, that's the key to the first brilliant solution. And there it is, the big aha moment. If an object asks for memory with new in its constructor right when it's born, then you can just put the matching delete call in its destructor. So now when the object naturally dies, the memory is automatically cleaned up with it. No more forgetting. This technique, by the way, is called RIII, and it was a huge leap forward for writing safer C++ code. But the story doesn't end there. That technique was a massive improvement. But the language designers knew they could make it even safer and way easier. They decided to build this safety mechanism right into the language itself, and that's how we got modern C++.
Yes, starting with a huge update back in 2011, C++ really evolved. The language itself introduced a whole new set of tools designed specifically to handle memory ownership and automate that golden rule, making those disasters we saw, well, pretty much impossible.
They're called smart pointers, and trust me, they are a complete game changer. On the left, you've got the old way. You, the programmer, juggling all these raw treasure maps, constantly worried about losing one or throwing it away too early. But on the right, you have the smart pointer. It's like a high-tech container that doesn't just hold the map, it takes full responsibility for it. It manages the ownership, guaranteeing it will handle the cleanup at exactly the right time, every time. Now, there are two main types you're going to use all the time. The most common one is unique pointer. It enforces a really simple rule, only one owner at a time. It's exclusive. When that unique pointer is destroyed, the memory is gone. Simple, fast, and incredibly safe. Then you've got shared pointer. This is for those times when you need multiple things to co-own a piece of memory. It just keeps a running count, and only when the very last shared pointer gives up its ownership is the memory finally deleted. So here's the crucial takeaway. The whole philosophy of modern C++ is safety by default. You don't start with the dangerous tool anymore. You start with a safe one, the smart pointer, and you only reach for those old raw pointers in very specific, controlled situations. This completely flips the script on C++'s old, scary reputation. And this brings us to our final thought. For decades, the conversation around C++ was all about the dangers of managing memory. But now, with these modern tools that automate the hardest parts, that whole conversation can change. We're free to focus less on just avoiding crashes and more on actually harnessing the incredible power and performance of C++. So the question is no longer, how do I avoid breaking it? But instead, what amazing things am I going to build with it?